Hello and welcome online SICB attendees. This is Andrew Burchill. I'm a graduating PhD student and myrmecologist, but it is time to get rowdy and raucous because I have reworked my talk since presenting in person, and you're about to get the new, improved version, untested and unapproved by my advisors. So let's jump in. We're talking about ants, transport, challenges, and walking on walls. So cooperation, it's really important. I probably don't need to tell you guys this. It allows groups to overcome challenges that individuals could never dream of. It's a fundamental property of the major transitions in evolution. It's key to the success of blood-sharing vampire bats or mobbing flocks of birds, swarm hunting, myxobacteria as well. Even your immune system and the cooperation between your cells, it's literally what holds your body together. But of course, my favorite, the queens of cooperation, are social insect colonies like ants and bees. However, of course, successful cooperation involves overcoming a host of other challenges, new challenges. In this case, we're talking about collective transport. So these ants here, they'll often work together to take food back to the colony that's too big for a single individual to carry. Ants at picnic, it's a big thing. So awesomely, this behavior has evolved independently multiple times across ants. They do this without any sort of leader and without any sort of verbal communication as well. Although it's really a charismatic behavior, it's not super well studied. There have been a few good studies investigating factors like transport efficiencies, recruitment, and obstacle avoidance. But almost all of these studies treat nature as this empty, flat plane, an abstract thing. But note that these ants have to traverse through some crazy environments. Like in this video here, they're going up a straight leaf, almost vertical. And of course, yes, they actually do vertical transport all the time. So this may seem intimidating to humans, but ants seem to just hit the wall running, so to speak, and they'll carry these loads up walls and along surfaces. So here are two highly realistic representative examples of animals moving heavy loads. Notice the difference between these teams and how they overcome the challenges associated with transport. See how they navigate across and around difficult terrain and against gravity. I want you to think about what makes these successful or not, and how can we tell? Essentially, we want to know, what is the measure of success for a group transport when they're performing? How do we rate it? So a lot of the time we'll focus on kind of individual prey like this cricket being taken back to the nest. But these massive colonies have thousands of foragers collecting many different prey simultaneously. So it's likely that the total intake rate of just insect meat is probably the more ecologically relevant quantity from the colony's perspective. Think of it as kind of a flow rate. Or you could think of it as a prey delivery rate, which is what we call it in the collective transport literature. You can think of kind of small prey as skinny pipes and just massive prey as these really wide pipes. And of course, the flow rate, or again, prey delivery rate, depends both on the width and then the speed of these transports. However, this is made up by a lot of other metrics that kind of work together and combine to determine the success. So we know, for example, that increasing a load's weight should pose a challenge to the transporters, right? So in this example of these Carabara ants with these different loads, what can we see and what would we expect to happen? Of course, there'll be more ants for heavier loads. That makes sense. Also, you could imagine these heavier loads actually move slower towards the nest. And perhaps the path they take is a little bit more circuitous and not as straight as these light loads. My question is this: what happens when we throw in the challenge of different inclines into the equation? Will a 90-degree slope, will it require more ants? Will the speed be slower? Will the path be straighter? How will this affect both these subcomponents and then the total efficiency as well? Additionally, there might be some logistical issues, with falling off of a wall, and there might be some interactions between different challenges. So in this case, we're going to be looking at weight and then incline, and I'm using crickets with these lead weights I attached to them, and I'm providing these ants with platforms of various angles to climb over. However, there are a lot of ants, and which one are we going to use? Well, I found some ants that love to perform. They love to transport. These beauties are the green Australian weaver ants, or Oecophylla smaragdina. They live in massive colonies of 500,000 workers. They live in the trees where they make these nests, and they forage on the ground and transport what they find up into the trees to feed their babies. My experiment was very simple. Essentially, I recorded these prey transport events in the field, or in this case, the suburbs, and I digitized what was going on, tracking the load and some of the individuals. We'll just jump straight into what I found, and we're going to be talking about this kind of prey delivery rate. So as the weight of these prey items gets bigger, how does the intake rate, or this PDR, the prey delivery rate, change? Turns out that heavier crickets have maybe a little bit more bang for their buck, or a higher return rate. However, as you get this higher rate of return from bigger prey, it requires more ants. So there's a little spending money to make money sort of thing. So the prey intake rate on a per ant basis probably makes the most sense to consider here. How much do you get, per dollar, so to speak? Well, with a limited number of foragers and cricket loads, how would you expect the per capita return rate to change as we kind of scale up the challenges? I would not have expected this to happen. Essentially, there were no changes. There were the effect size, man, it is freakishly small. Their efficiency per ant in these groups is constant across all angles and all weights, every challenge we could give them. It's super freaky and not what I would expect, but my more intelligent collaborators say that these ants are actually probably behaving optimally. And this is what we would expect if they were really, really good. It's a bit much to take in at once, but you can talk to me later, and I will even mention this stuff at the end of the talk as well. But moving on, what is going on under the hood? So how are things changing in terms of ants and speed and straightness of the path? How do they combine to make this really weird result? Pretty much in terms of weight, it's what you'd expect. So heavier requires more ants, it goes slower, and the path isn't as straight. Yeah. We kind of already knew that from past studies, but we're talking about weight and incline. So we're just going to jump to incline. So it turns out that steeper inclines do have more ants involved. This is the trend for the light kind of weighted crickets, but the pattern is across all weights. Interestingly, though, it doesn't affect the total average speed. So vertical surfaces, and they go up those bad boys just as quickly as they do over horizontal surfaces. And now if we look at the kind of the path straightness here, as you can maybe see from these representative examples, it does get a little bit less straight as you go onto a vertical surface. That means the cricket travels a longer, more sinuous path to achieve the same total displacement. And you may have noticed in this, there's this curious little loop here in this one. And if we review the video, we can see the source. Yes, it turns out these ants are not perfect transporters, and they do occasionally drop the load a bit or at least slip backwards. But what explains this? So it turns out that it's almost all incline. With really light loads, it doesn't matter at all, but essentially they'll backtrack more or slip and fall on vertical surfaces. Again, like that's nothing new. We would expect that maybe. But what happens? So how do ants compensate for this? Forgot about that. So because we saw on steeper inclines, there's these setbacks because they take longer paths, there's more slipping and falling. So why don't they have slower total average speeds? Well, it turns out when we exclude these following events, the average instantaneous moment-to-moment speed in any single direction is actually faster on vertical surfaces. I kind of call this the hustle, but they're moving faster to make up for these setbacks on inclines in such a way that it balances out. That's kind of weird. How do they do that? I have a few mutually non-exclusive hypotheses. Perhaps the individuals are maybe trying harder on the vertical surface, or maybe it's just because there are more of them. So for my kind of quality hypothesis, there's some evidence that say individual ants, when they remain grabbing onto the load for longer, it actually helps. Their persistence could minimize some of these things. But I use survival analysis here, tracking how long these ants remain engaged with the load, and there is no difference. But maybe there are more ants. So we did find that as the number of ants increases, the transports do move slightly faster. So maybe incline's effect on speed is really just a result of more ants. So this quantity hypothesis, essentially saying, no, incline is not affecting speed. It affects the number of ants, and then the number of ants affects the speed. I used something called a mediation analysis to test this, and compared both of them at the same time. And it turns out that when we look at these things together, incline doesn't really have a statistical effect on speed, and it's probably mediated through the number of ants involved. That's cool. So essentially, what did I find? Well, the efficiency never suffers no matter what challenge we give them. And I mean, 10 times as much weight on a vertical surface, nothing. It's super weird, whatever. We'll talk about it more if you want. We also found that vertical transport does have some challenges that are unique to it. There's slipping, there's longer paths. We also found that it seems to essentially never interact with weight. They're two separate challenges. We found that ant teams seem to just kind of hustle faster to overcome these problems, probably because more ants are involved on a vertical surface. Why are more ants involved on a vertical surface? How do they know? No clue, but that's for the future. So you have two options now. You can either watch the acknowledgements and simply end the talk there, or you can continue watching, go deeper down this rabbit hole with me, and I'll talk about some of these weird, spooky results. Also, I'm looking for postdocs, so hit me up if you're in the Southwest and you're interested in behavior or insect research. So I'd really like to thank my fiance and lab assistant, Kelly O'Mara, as my many collaborators as well, and the National Science Foundation and the Australian government. So if that's all, you can head out, but if you're interested, you can stick around. Okay, now that the like lame people are gone, let's talk about the cool stuff here. This is a little bonus content. So as I said, there's this really freakishly constant PDR per ant, and using some Bayesian analysis, we can say it's essentially zero. You can't really prove the null, but we can say that it's biologically negligible. And so one of the things that may be happening here is something called the ideal free distribution. Imagine we were in person and there were two free coffee tables at the conference. One was serving Starbucks and one was serving McDonald's. If my advisor showed up, as many of us would, we'd probably go to the Starbucks one first because we prefer that one. And if my other advisor would show up, he would probably get in line too, because it's still worth that small wait. And as more and more advisor clones show up, though, at a certain point, one of them will say, it's not worth it. Let me head over to the McDonald's. And then as people kind of accumulate, you get this situation where the rate of return per unit time is the same in both of these different patches. So this is something that could kind of be happening with my ants. The ants are kind of going to different loads and engaging with those loads based on this kind of rate of return. And so across the loads, you see this constant PDR per ant. However, instead of kind of coffee preference, it's really the colony preference of individual contributions to loads in comparison with other loads. And so it's actually, we have no idea exactly how this works, but the ants are kind of, could be, I guess, sensing whether their contributions to an already moving load are helping enough and increasing that marginal utility, or if they're just kind of not needed and they're not getting a good bang for their buck. Another interesting thing is when this relationship could be a balance or a trade-off between the weight per ant and the average speed of the loads. So there's this amazing 1/x relationship where as the weight per ant increases, the speed of the load decreases. And it has this cool kind of thing where PDR, or the prey delivery rate, is essentially multiplying these two values together. And so the area under the curve for any particular value, whether it's a light load or a heavy load, the area is kind of the same. This PDR is constant because of this trade-off. Yeah, I have also kind of looked through the literature to see if I can see this happening in other ants. There's some indication that that may be happening, but we'll need, honestly, a lot more data. So thank you for sitting through this kind of bonus section. As a reward, I have this randomly rotated video of crazy ants transporting a cricket over a horizontal and vertical surface. And if you can tell which is up and which is sideways, I would be impressed. I cannot. It's really hard to see if they're behaviorally doing anything. So yeah, thank you so much for my talk. I hope you have a wonderful January. Yeah, and yeah, thank you.